And we're back talking about roots of variable expressions. And this time I wanted to put a fraction in there and show you an example where there is some simplification to occur first. And let me just make that as a recommendation. When you look at the root of a fraction and you want to, quote, simplify it, then look at the inside first, the fraction itself, and see if you can simplify anything there. Look at the numbers to see if they reduce. Look at the variables to see if somehow they combine using the exponential rules. And indeed, that's the case here. Let me continue. I'll keep my root symbol. I'm going to look at the numbers first, the 8 and the 7. Those don't reduce by a common factor, so I'm just going to leave my 8 here and my 7 here and then see what happens with the rest. X squared over x to the 5th, we can do some using of exponential rules there to simplify that, and that's going to come out to x to the 3rd power. And take a look at those exponential rules to review that. Y to the 5th over y simplifies to y to the 4th. Okay, that looks great so far. I would call this pretty simple, at least it looks simple. But some people don't say that that's simplified. So let me continue with this and see if we can end up with this, quote, simplified thing. And I'm going to start by calling this the root of the top, 8y to the 4th, over the root of the bottom, 7x cubed, and see if I can take the root of some of these things. Certainly the number 8 has a perfect square factor, namely 4. Okay, so I can call this instead the root of 4 times 2 instead of 8. 4 times 2, y to the 4th. And on the bottom, there is no perfect square factor of 7, but x cubed has within it an x squared. So I'm going to call this root 7x squared times x and continue from there. So on the top, I can take the square root of 4, that is exactly 2. So a 2 comes out. Y to the 4th power, since we have an even power here, and we're taking the square root, 4 divided by 2 is 2, so I get a y squared out here. I'm left with square root of 2 on the inside. The bottom, the square root of x squared is x, so I can take that out, and I'm left with the square root of 7x, like so. Now, some people insist that we do not have a square root in the denominator of a fraction. So I'm going to multiply this result by the number 1, but a very special one, and it looks like this. The root of 7x in the denominator and the root of 7x in the numerator. When you have anything over itself, that is equal to 1. I chose the root of 7x because root of 7x times root of 7x gives me just 7x. It gets rid of that root symbol there. If this were a cube root, then I would have to do it 3 times to get rid of the root symbol, and so on and so forth. There are other clever ways to not have to repeat yourself, but let me just continue from here and see what we get. So, on the top, 2y squared. Root 2 times root 7x. Remember, when you're multiplying a couple roots, you can just use one root symbol and multiply the insides to get something on the inside. So this would give me then 2y squared root 14x on the top, and on the bottom I get an x times 7x, the root symbol goes away. And I'm going to continue to simplify from there. To obtain 2y squared root 14x, nothing really more to do up there. On the bottom, x times 7x is 7x squared. Now, some people, and probably the biggest mistake people make, is they want to do this 14 on the inside divided by this 7 that doesn't have a root. Now be careful with that, because this is not 14. It's the square root of 14, which is some other number, not 14. So you cannot do 14 divided by 7 here. In fact, I'm going to call this my fully simplified result. And please consult your textbooks and talk to your professors to find out what they're calling fully simplified. There is not a radical down here, and some people like that. So let's leave that one alone for now. You can have a conversation with your math pals over it. Let's take a look at something that comes up often in the Pythagorean theorem. Quite simply, the square root of a squared plus b squared. Remember, Pythagorean's theorem is for right triangles. It says a squared plus b squared equals c squared. And if you're solving for c, you take the root of both sides, and you get something that looks like this. Now, the question is, can I simplify that? The answer is no. This is it right here. The mistake people make is they want to say, oh, that's square root of a squared is a, the square root of b squared is b, so isn't that equal to a plus b? Well, let me tell you, it is not equal to a plus b. How can I say that so confidently? Well, consider this one instead. The square root of parentheses a plus b with a square on the outside. Now this one indeed is just a plus b. How come? Because the square root of something squared is itself. Now, we know that this one's true. If you're trying to say that the other one also gives you a plus b, then you're indicating that these two expressions are the same, but they're not. In parentheses, the a plus b squared, if you were to expand that out, gives you a squared plus 2ab plus b squared. That becomes what we call a perfect square trinomial. So indeed, they're different, and I invite you to play with that and have fun with it on your own time. So I hope you've been having fun so far. Stay tuned for more videos.